Hey guys, just thought I'd put another video together here. I actually went back to this experiment. I was having more luck with this. I was kept going down rabbit holes, you know how it goes. Anyway, so I rewound this coil. So remember, this is the one with the ferrite toroids that I don't know if you can see in there. They're all just a bunch of them stuck together. You know, like they're these things. And so what I've done, I actually unwound these. I've wound this a few different times, but right now I've put the windings back on where I have 1, 2, and then the red coil is 3. The red coil is the input coil. So we have L1, L2, and L3. What I did though is on the center, I don't know if you can see here, see this bit here and this bit here of this coil, there's 7 turns of each of the L2 and 3 that are wound back, so that gives me the non-inductive parts of the coil. And so I had those on the outside, and I wasn't getting very good results, so I've rewound this and I've got the non-inductive parts on the inside now, and I find that it works much better for some reason. So these are opposing, the L2 and L3, so that's our little diagram. It's actually more like this. So I measured the length of these, alright, so I'm trying to work off the wavelength frequency. Let's go through it. So the L1 is 4.1 meters. It's about 8 centimeters too long at the moment. L2 is 8 meters, 8.05 meters. L3 is 8.08 meters. Okay, so they're a little bit different. The first layer is 17 turns, second layer is 11 turns with 7 turns the opposite way. Okay, so they're both wound the same, but the non-inductive part's in the middle. So if we look at the wavelength of 8.05 meters, that's 37.241 megahertz. Okay, a thousandth of that would be 372 kilohertz. So 372.4 kilohertz. 444 harmonic would be 838.76 kilohertz. So I'm trying to use harmonics of those wavelengths in this coil. And then also what I've done on this coil is on the L1, so the red, I've actually added a capacitor. Okay, right now it's in parallel to the input, so like that. And then also on the L2, I've also got that in parallel. They're both 2 nanofarads. So I have the L1, that's going to resonate at 838.82 kilohertz. And the L2 is going to resonate at 375.13 kilohertz. Okay, so you can see I have harmonic. They are tuned to harmonics of. Well, they're pretty close anyway. I think it can be actually a lot better, but I'm just trying to get see what results we can get here. We'll just kind of get it close enough. You know what I mean? Anyway, with that said, if I flick this thing on right now, I just want to show you at a low frequency what we're seeing on the scope. And if I turn it on, okay, we got 2.9 kilohertz. Okay, you can see I got a nice triangular wave there. That's actually here. That's on the L3 coil. Okay, but you can see I got a nice bright light. They're a little dim on the inductive bulbs. This is an LED bulb, but this is just to show you the triangular, the sawtooth wave, okay? Because I'm going to be running it at much higher frequencies, and that's when I seem to get the better results, just the way that I have this thing tuned. So I'm going to now come back to you in just a sec. Okay, so I've got it all set up now to the frequency a harmonic frequency of the wavelength. So I have the frequency set at 838.82 kilohertz. The duty cycle's 32% right now. I have a square pulse going in. The input voltage is going to be 26 volts. Coming into our MOSFET, and then you can see the 5 volts here is just to drive the board. I've got the probe across the 0.1 ohm resistor. Okay, this is the pink trace. Okay, that's set to 1 times. You can see the pink trace there is on 10 times. Okay, so the 10 times on the scope, 1 time on the probe, going across the 0.1 ohm resistor. That's going to give us our amperage. And then the voltage probe is across the bulb. Okay, so it's just directly across the bulbs to see what our voltage is there. The L3 coil, you can see, is just the diode in for that on that side of the coil. So I've just been playing around doing a couple of different, duty cycles and voltages, and different load with either this is an LED bulb, which is 12 volt, 7.5 watt LED bulb in here. And what's interesting, it seems like depending on what duty cycle you have it at, what voltage you have it at, obviously the frequency makes a difference, and they're all so interrelated that it's quite fiddly. You're trying to find the best combination. So I'm trying to keep the frequency at what I think is a harmonic of the wavelength frequency to make this work, and I'm just been mainly playing with the voltage and the duty cycle. Anyway, so if I turn this on, I just had this on stop for a sec, but let's turn this on. Okay. All right. So now you can see we've just got 2 bulbs lit up. Okay. These are just regular bulbs, regular, I guess, flashlight bulbs. And you can see right now we got 10.2 volts, okay, across the bulbs, and we got basically 2 amps on the across the resistor here. So you see that's well, here I've got 11, so I didn't do, but yeah, 10 volts and 2 amps is 20 watts, all right? That's what's coming out. Here we've got, what's that? 15, 17, about 17 watts going in. Okay, that's even if you include what's driving it. So we've got it. We have 20 watts out. So there's a little bit of an increase there, not a lot, of 3 watts. What's interesting though, if you plug this bulb in, and this is going to change the impedance. Okay, now we got that 12 volt, 7.5 watt bulb. The voltage actually goes up. Now we're nearly at 12 or 11.5, and the RMS for the amperage has gone up to 2.5, 2.6. So 11.5, 2.5. That's 28.75 watts out now, and we've still got 18 watts in roughly. That's it. That's if you count what's driving it. So that's a 10 watt increase there, which is pretty nice to see. The nice thing to see on this is, I think it's important, if I take out the L3 diode, disconnect that from the circuit, boom, she's dead. I've got nothing. Oh, tiny, just tiny bit of glowing. Obviously the current draw drops down, so I think this can be improved. Put that back in, and obviously the circuit lights up. I did notice, if I jump this diode out, I was getting a slight increase, but it depends on what I had the duty cycle and frequency at. Sometimes it actually gives a decrease. So it is quite fiddly. You do have to really play around with this to try and find your you know, where you're going to get your best output. But you know, it's not really making much of a difference at this particular frequency and duty cycle. And also the voltage. You know, right now I've got 26 volts going in. So, you know, if you change that up and down, it also makes a big difference. So, anyway, I just wanted to give you guys an update on where I'm at on this. And I do appreciate, Chris, your help. I kind of went off down different rabbit holes again, and Chris said to me, just go back to what you would have success with. So this is it's been good advice, and he's right. Just keep it simple. I think we're well on the right track here, and I notice if I increase the voltage even more, you get, you know, a bigger delta on the extra wattage out. So, you know, obviously I don't want to run this MOSFET too long. It just gets hot, and I don't have a fan or anything on this. So, but right now I've just turned the voltage up to 31 volts. Okay, we've increased the duty cycle slightly to 35%, keeping the frequency the same. But if we flicker on, all right, and then these are fully lit, overlit, if anything, and we got, you know, over 15 RMS on the voltage. Stop that for a second. And 3.1 on amps, but it's pretty damn, yeah. So let's just say 3 amps on the RMS and 15 volts. Okay. So what does that give us? 15 volts and 3 amps. That's 45 watts out. So that's like an extra 20 watts. And in we got like 24 going in. That's if you count the what's driving the MOSFET. Also, just to go over the oscilloscope settings that I have this on. So obviously I'm, you know, trying to make sure I get the most, you know, accurate reading I can. I think the most accurate reading for the voltage for the bulbs is across the bulb. Okay, obviously going across a fixed value resistor, you know, should tell us our amperage. And then the other thing that I've done is I've been looking at the, let's turn this on a second. Okay, so we're lit up, and then if I go through on the acquire mode of this scope, you can see you can change your modes from high resolution, you know, normal setting, the peak settings, and your averaging. And so I believe that gives me pretty accurate readings, and they're nearly exactly the same, or no matter what. Normal of giving 15 volts there. Peak, still saying 15. Average, it drops down a little to 14.3, so I'm losing a volt on averaging, which is probably actually being pretty accurate. And then the high resolution, you know, 14 to 15. So, and that's obviously changing the sampling of your signal. So, you know, there's all the ways that this scope is sampling. So I think my readings are pretty accurate. If anyone has any comments on that or concerns, don't hesitate to comment. All right, thanks.